Stop putting everything in a Go routine. You may think throwing more concurrency at a problem will speed it up, but there's a bunch of cases where it will just slow it down. So let's look at some of those cases and fix how you approach concurrency. This was a super fun one to plan, so get excited. Our first case is the most straightforward. What happens when you apply a concurrency pattern to operations that are already very cheap? For this example, I'll compare some simple sequential operations to the same operations performed in a pipeline. So let's take a look. Here I have a simplified run function that's used to run each stage of the pipeline, and a few easy transform functions that will act as each stage. And if you want a more detailed look at how to set up pipelines properly, check out my previous video, link in the description. Now, the sequential version of this is going to be super simple. We're going to take in an input channel, do all of the transforms in order, and then return a slice of results. So first we'll create the output slice, then arrange over the input channel, run the 3 transform functions, and append the value to our output slice. And we just need to return it. Cool. Super, super simple. Now we'll do the concurrent version, which still accepts an input channel, but also accepts a number of workers, which will set how many Go routines are run for each step of the pipeline. And again, we're returning an int slice. So we need to run each stage of the pipeline separately. And the run function takes an input channel, a transform function, and the number of workers. And then we do the exact same thing for the rest of the operations. Now we need our final output slice. And then we're going to range over the last channel in the pipeline and append each value to the output slice. So now let's benchmark these 2 functions and see what happens. I'll make a full video in Go on benchmarking in the future, but for now I'll just walk you through the benchmark functions I've put together. In this case, I'm using a quick helper that I made to get a slice of 1,000 random integers. We run a benchmark on the sequential version first, and here I'm using another helper to populate the input channels from the slice. Then I'm benchmarking the concurrent version using 5 different values for the number of workers. And so now when I run this benchmark, the concurrent pipeline with just 1 worker takes about 5 times longer than the sequential version does. And as we add more workers, the time it takes just gets longer and longer. So the moral here is don't throw Go routines at a problem unless you have a measurable reason to do so. If the tasks done in each Go routine are too small, then the overhead from Go routines, channel communication, and scheduling will outweigh any benefit you get from concurrency. And it's also easier than ever to make multiple iterations using AI, so there's no reason not to measure and optimize your code, especially for hot paths. Okay, so let's look at a case where concurrency actually helps. For this example, we're going to take in a slice of ints and return the sum of all those ints. We're also going to use a work function I put together that just simulates an expensive operation doing a bunch of random math. So in this sequential implementation, all we need to do is range over the input slice and add up the results of our work function and return the total. Oops. Now to speed this up, we'll have a concurrent version that still takes in an int slice, but also takes in a chunk size. Then we can split the slice into chunks and run each chunk concurrently in different Go routines. And again, we'll return the final total. One key point here is that the lower the chunk size, the higher the number of Go routines will be. And that'll be important later. So for the implementation, first we need a wait group. Then we need a slice to store the totals from each chunk. And the length of this slice is going to be the number of chunks. Okay, now we need a separate variable to keep track of what chunk we're on. Then we're going to do a bit of a different loop, where on each iteration, we're going to increment by the chunk size. And we do that so we can get the correct start and endpoint of the chunks in the slice. Quick little check here. Reassign the chunk counter for non-buggy closures. And we're finally going to start a Go routine. And it'll look pretty similar to the sequential implementation, but we're going to loop from start to the end index. Then we're going to add up the totals for each of the numbers in the chunk. And instead of returning the total, we're going to add the total to our chunk totals slice. Then we increment the chunk counter so that this applies to the right index. And now we wait. Then after all of the chunks have been processed, we're going to add up and return the final total. So let's benchmark this. In this case, we're getting a slice of 10,000 random elements. Then we run the benchmark for the sequential version. Then we do the concurrent version, and we're doing it with a bunch of different chunk sizes so you can see the difference. And for clarity, the number of Go routines is going to be listed in each benchmark. So now we run the benchmark, probably fast forward. So this top one is the sequential version, and this is how long it took. But when we do the exact same operation with 2 chunks and 2 Go routines, the performance is almost 2x better. And then as we add more Go routines, the performance starts to get better and better and better until somewhere between 200 and 400 Go routines, performance starts to get worse again. And then when we jump up to 1,000, it gets even worse. So while concurrency helps a ton in this case, the benefit isn't infinite. So it's generally a good idea to tune functions like this for your specific workload. If you split the work up so much that each Go routine is doing just a super small task, then the scheduling overhead from all those Go routines will start to degrade performance. Okay, the next example is going to use the same sum concurrent function from that last example, and we're going to add a couple more functions to compare against it. The only change we're going to make here is removing the work function to make the changes more obvious in the benchmark. The first new implementation is going to do the same thing as sum concurrent, but we're going to use atomic operations. So we won't need this anymore. We're going to have a single total variable, and this loop will look pretty much the same, just a bit simpler. We won't have a local total, and for each number in the chunk, we're going to add it to the global total using atomic.addInt64. And we can get rid of this. Awesome. Now the next implementation will be almost the exact same as this one, but we're going to use a mutex lock instead of atomic operations. So in addition to the global total, we'll have a mutex. And then here, instead of doing the atomic operation, we're going to acquire the mutex lock, add each number from the chunk to the total, and then release the mutex. And back to the benchmarking. We have a slice of 10,000 random ints, and we're using a bunch of different chunk sizes again. Then for each chunk size, we're running a single benchmark for each of those 3 functions that we have. And now the big reveal. All right, I had to fast forward that one, but let's check out the results. Now you can see no matter what the chunk size or how many Go routines there are, in each case, using the version with atomic operations is way slower than using the original version. And using the version with the mutex is even slower. The reason for the slowdown is because of atomic or lock contention between the Go routines. Only one Go routine at a time can perform the atomic addition or acquire the mutex lock. So the Go routines end up fighting and bottlenecking each other, which degrades performance. The takeaways from this example are to try to avoid having multiple Go routines share memory like this. And if you need to share memory, go for atomic operations first. Then, if you need to coordinate multiple values or have more complex logic, you can jump to using a mutex. All right, the next example is a bit more of a complex case, so I tried to simplify this example as much as I could. We're going to look at false sharing and its impact on performance. And the basic idea behind false sharing is that no Go routines are accessing the same memory, so no synchronization with atomics or locks is required. But the values that each Go routine accesses are stored close enough together in memory that they're saved in the same cache line on the CPU. To explain that further, each CPU core has its own cache. And the cache stores memory from RAM in blocks called cache lines. So there are multiple cache lines in the cache, but each cache line can hold multiple values. Now, if another core caches this same cache line, then each time a Go routine running on either of these cores modifies one of these values, this specific cache line will be invalidated on all the cores that it's stored on. So if you have multiple Go routines modifying values in the same cache line, what you end up getting is this ping pong effect of cache invalidations as the Go routines write to the same cache lines, which makes the cache optimizations done by the CPU harmful instead of helpful. Okay, so to demonstrate this, we're going to start with a super simple counter type, and it's just going to have an int64 count. Then we're going to have 3 implementations of a counter function. The first one, again, is going to be a sequential version, and it's going to take the number of counters we want and what number we want to count to. And then we'll return a slice of counters. So we'll make the output slice and run a nested loop that will count up to count to for each counter. So we'll get the current counter, do our nested loop to count. And to actually do the counting, we need to do it explicitly to prevent some compiler optimizations. So I'll throw that in a quick function up here and then call that function in our loop. And last, we just return counters. So that's the sequential version. The concurrent version looks super similar. The only difference is we're going to add a wait group and count on each counter in a separate Go routine. And then we need to wait for all of the Go routines to be done. So this version should run faster than the sequential version, but we can do better. On my computer, the cache line size is 128 bytes. So we're going to make a new type called padded counter, and we're going to pad this struct with a byte slice of 128 minus 8 bytes. And I do that because the cache line size on my machine is 128 bytes, and the size of an int64 is 8 bytes. Now, theoretically, the padding will make each instance of this struct live on a different cache line, meaning there should be no cache invalidation between different cores when we update the count. One extra thing to note here is that most computers have a 64-byte cache line. So you need to know where your code will be running to use this technique. All right, now to use this type, I'm going to copy this function, rename it, and we'll just swap out the counter for the padded counter type. And now the benchmark. This one's pretty simple. We're going to count to 1,000,000, and we're going to do it go max procs number of times. And I'm using that value so we'll have the same number of Go routines as the number of logical cores on my computer. Then we have a single benchmark for each of the functions. So let's do this. All right, we get exactly what we expected. The sequential version is the slowest. The concurrent version without the padding has the false sharing and is the second fastest. And then when we use the padded struct, it speeds it up a ton more. This issue is 100% more niche than the rest of the examples, but it's still important to know about when you're optimizing your code. Ideally, you can just try to avoid this issue altogether by not modifying values that may share a local memory space with each other from different Go routines. Or at the very least, try not to group things into a slice like I did here. But if you really need it, this padding technique works. And that is all I got for you. Thanks for watching, and if you learned something, maybe subscribe to learn more stuff. As always, keep breathing, keep building, and I'll see you next time. Peace out.